Hello everyone, my name is Huanyu Zhang. Today I would like to introduce our work on differentially private Assouad, Fano, and Ziteng. This is a joint work with Jayadev and Ziteng. We are all from Cornell University. This is the syllabus for our talk. I will firstly talk about problem formulation and then move to our main results. Finally, I will introduce a toolbox for proving DP lower bounds. I will start with the problem formulation. The problem we look at is statistical inference, which lies in the following framework. Given samples from an unknown distribution, we want to infer the property of the unknown distributions. There are several examples. First, distribution estimation problems. Second, hypothesis testing problems. For example, we want to test whether the unknown distribution P is a uniform distribution or not. Third, property estimation problem. For example, we want to estimate the Shannon entropy of the unknown distribution. Formally speaking, let n be the sample size, and capital P be a collection of distributions over Kelly graph X raised to n, which is the space for n samples. And here, theta P is the parameter of interest, and L is the loss functions. The objective is that given random samples X from unknown distribution P, we want to estimate theta P. And we can define the minimax risk as follows, which is defined as the optimal performance of the optimal estimator, which minimizes the worst case estimation error. So there are two sub-problems from statistical inference, where the first problem is distribution estimation. Here, we let P equals Q raised to n be an n-fold distribution, which means that for each fold is independent. And also, for the parameter theta P, we just require it to be Q. And here, the objective is changed to the following. Given IID samples from Q in Kelly graph Q, we want to estimate Q itself. There are several classes we will look at in this talk. The first distribution class is K-area distributions, where Kelly graph Q is just a simplex of K. And second is the product distributions, where Q is a set of product distributions over K raised to D, which means that there are D dimensions, and for each dimension, it can take up to K values, and each dimension is independent. A final class is a Gaussian mixtures, where Q is defined as a mixture of K Gaussian distributions in R raised to D. Okay, another sub-problems of statistical inference is hypothesis testing. So let P1 and P2 be two disjoint hypothesis classes, and here we just restrict theta, capital theta to be a binary parameter space, where theta P equals I for P from capital Pi. And here loss function is a binary loss functions. The objective is that given some random samples from unknown distribution P, we want to test whether P comes from capital P1 or from capital P2. We can also define the minimax test error, which is a classification of error of the optimal tester, which minimizes the worst case classification error. These are classic statistical inference problems, but there are some new challenges. One challenge comes from privacy. As we all know, data may contain sensitive information. For example, in some real applications, like in navigation or in medical data are highly sensitive. So it remains an interesting problem on how to carry out statistical inference and meanwhile protect the privacy for individual users. So there are many notions for privacy, so of which the most famous one is differential privacy. We see a randomized algorithm. Here is just our tester or estimator f hat is epsilon delta dp. If for any neighbor dataset d1 and d2, here neighbor means that they differ at only one place. We see f hat is epsilon delta dp if for any even s, the probability of f hat d1 in s and the probability of f hat d2 in s is similar. When delta is 0, we name it as pure dp, and when delta is not 0, we name it as approximate dp. Now, it comes to our main objective. We want to characterize the minimax risk in dp estimation and testing. Similar with the non-private version, we define the minimax error for the epsilon delta dp estimation. So except that it's similar with the non-private case, except that we require our estimator theta hat is epsilon delta dp. Similar case for the classification error for the epsilon delta dp testing. Okay, now we introduce our results. In one sentence, we establish a toolbox for proving lower bounds in DP statistical inference. Specifically, we generalize classic tools to the DP setting. We apply our toolbox in pure DP distribution estimation, and we look at and we derive tight bounds for the following problems. For the first problem, which is estimating K-area distribution in L1 distance, we apply our epsilon DP Fano inequality, and which will be introduced later, and we derive tight lower bounds. For the other problems, such as K-area distribution estimation in L2 distance, estimating product distributions, and Gaussian mixtures, we derive almost tight results, which are tight up to logarithmic factors. Similar results are shown for the approximate DP, which can be viewed as corollary for our epsilon delta DP Assouad method, which will be introduced later. So for the K-area distribution estimation in L1 distance, we get the optimal results. And for the other problems, we get almost tight results, tight lower bounds, which are tight up to logarithmic factors. We want to mention that these results are very important because it's generally very hard to prove lower bounds in epsilon delta DP estimation problems. The only known tool to prove epsilon delta DP lower bounds is the fingerprinting lemma. However, it's not clear how to apply it into K-area distribution estimation, which is one of the most important problems in statistical inference. We believe that our newly established tools can be viewed as a good supplement to the current tools of proving DP lower bounds. Okay, now I will introduce our toolbox for proving DP lower bounds. All the tools are based on the same observation. Suppose there exists some coupling between x and y, where x are some samples from distribution P1 and y are some samples from distribution P2. We suppose there is some coupling between P1 and P2, which means that, generally speaking, x can be converted to y by changing d coordinates. Here, d is the coupling distance between P1 and P2, and is defined as the expected Hamming distance between x and y. Finally, by the group property of differential privacy, informally speaking, we can say that we can build a connection between theta hat probability of theta hat x in S and the probability of theta hat y in S. And we can imagine that, suppose d is very small, in an extreme case d is 0, we require that, this equation requires that theta hat should be exactly the same with theta hat y. And on the other hand, if we let d to be very, very large, which means that it's easier to distinguish between P1 and P2, then it has a very loose constraint for the probability of the probability distribution of theta hat x and theta hat y. Next, let me introduce our toolboxes. The first tool is the DP-Lee-Helms method, which can work for both approximate DP and pure DP. However, it can only apply in binary testing problems. Let P1 from capital P1 and P2 from capital P2, and XY is a coupling with the expected common distance bounded by D. Then we can show that the private classification error can be lower bounded by the maximum of two terms, where the first term is just the one-man total variation distance between P1 and P2, which comes from the non-private Lee-Helms method. The more interesting result is the second term, which is associated with, which is connected with d, epsilon, and delta. This is the error incurred due to privacy. So, and it can be shown that when d is very large, the error incurred by the privacy is very small. So, DP-Lee-Helms method is a powerful tool. However, it can only be applied for the binary testing problems. And therefore, a natural question is that whether we can develop some tools which works for multi-way classification and even estimation problems. Thus, we developed DP Fano inequality, let V to be a subset of distribution space, to be P1, P2 until Pm, and we further require that for different pair, for one pair of distributions like P and PG, their parameters are well separated, and we further assume the KO divergence between P and PG is small. Then, by the non-private Fano inequality, it can be shown that the estimation error can be lower bounded by the first term, which is alpha over 2 multiply 1 minus beta plus log 2 divided by log I. However, the more interesting result is the second term, where we further assume there exists a coupling between Pi and H for each pair Pi and Pg with a coupling distance d. It can be shown that it can be bounded by 0.4 alpha and multiply the minimum of 1 m divided by e raised to 10 epsilon d. This is the cost due to privacy. We will also want to remark that the dp Fano inequality can be viewed as a probabilistic packing lemma, where we change the coupling distance into the coupling distance. So it can only give us meaningful lower bounds when delta is small or even pure dp. Finally, we show a dp Assouad method, which can be used for both pure dp and approximate dp. It can also be used in multivariate classification and estimation problems. However, it has some requirements on the loss functions. Let V be a subset of distribution space P, and which are indexed by some like epsilon k, which is defined as the plus 1 minus 1 raised to k, which has all the k bit strings. And we further assume that L is an additive loss functions, which means that for two vector u and v, theta pu and theta pv, the loss between them can be measured by how many bits u is different from v. Then we introduce our dp Assouad method. If there is some coupling between p plus I and p minus I with coupling distance d, then we can show a lower bound of the estimation error, where p plus I and p minus I are just a mixture of distributions, where the ith position takes either plus 1 or minus 1. And thanks for attending. These are all for my presentation. So please refer to our online version for more details. Thank you very much.